Hi everyone, this is Team 25511. We're titled the SEMILITHO, which stands for Semiconductor Lithography Tool Prototype. My name is Natalie Islas, I'm the team lead and I'm a systems engineering major.
My name is Josiah Rash, I go by JD. I'm a mechanical engineering major and I'm the mechanical lead as well as the procurement lead.
Hello everybody, my name is Travis Reyna. I'm an electrical and computer engineering student and I am the computer engineering lead.
Hi everyone, my name is Max Henderson. I'm an electrical and computer engineering student and I'm the electrical lead.
Hello everyone, my name is Adel Ansali. My major is electrical and computer engineering and my role is the software lead.
Hi everyone, my name is Marian Majnouni and I'm material science engineering major and I'm the design lead.
Semiconductors are currently being heavily invested in. This is due to the fact that they're found in almost every electronic device we have. As technology advances, there is a need for faster processing and more powerful microchips. One of the biggest issues is providing the workforce for these emerging semiconductor manufacturing companies. This is due to a variety of reasons, but does include the lack of industry exposure to students. Let's do a quick overview on the photolithography process. First, we begin with the wafer and we coat it with photoresist. The next step is to spin coat it. So once we add that photoresist onto the wafer, we're going to spin it extremely quick. In our case, the lab that we partnered with spun it at 3,000 revolutions per minute. This ensures that the wafer is uniformly coated and that the photoresist is evenly distributed. After this, we use a UV light, and in our case, we are using a projector to project our pattern onto the coated wafer. After the pattern is projected onto the wafer and the UV light is on for a sufficient amount of time, we then go back into the clean room and verify that the pattern was successfully imaged onto the wafer. This is done using a series of chemicals and processes that our lab is responsible for. This is not within the scope of our project. Our project is simply the patterning portion of the photolithography process. Now that you have an overview of the photolithography process, let's dive into our project goal. The goal of our project was to develop a tabletop, compact, simple, and portable photolithography tool prototype. This prototype has to be capable of patterning on a micron level scale. The main purpose of our tool is to serve as an education and training resource for the semiconductor device fabrication in coursework and outreach activities at the University of Arizona.
In this section, I will be going over the system requirements and the system requirements verification table. For system requirements verification table, we have divided it into 4 main subsystems. 4.1.0 compact design. The second main subsystem is 4.2.0 performance. 4.3.0 safety. 4.4.0 interface.
Because we want to make this project accessible to high school students to kind of get them engaged with the photolithography world and just kind of nano devices in general, we want it to be very simple for them to use, which is why we ended up going with digital photo mask. Basically, the digital allows them to connect with it via their computer and then kind of change the mask as they want. Once they've done that, they can turn it on essentially and engrave on the disc, and so that's what we wanted.
On the side there, you can see a little circle. That's our engineer interacting with the user interface. For the XYZ stage, we have our XYZ software going to our mechanical motion system, which controls the XYZ movement of our stage. For patterning instances, it would move the stage for different patterns being imprinted onto the wafer. We also have our flare camera, which is our alignment camera. Within our optical module, there is a beam splitter that splits 50-50 the image coming out of the DLP, which is our digital light projector. The whole main thing goes back to our DLP. This digital light projector is essentially what modulates our image into light.
For our everyone, our aim was to have a precision movement and automated movement. For 4.2.2, for our automated movement, we passed, as you can see in this video, and also for 4.2.3, we also passed, and you can see it in this video. For another verification, we had the paperclip attached to our stepper motor to verify if it's actually moving to the numbers that we have.
Here I'm going to be explaining the MVP2, which is the requirement for 4.2.1, which is micron scale precision. We did reach this with a value of 11.93 microns, which is within our range of plus or minus 2 microns from 10 microns. We did this by analysis, and here we can see the image we used using the DLP and the camera software. Here we can see we passed through a 5-pixel width strip of light, and you can see in the background we have a precision ruler which has 0.5 millimeter tick marks, which is 500 microns. We then use the software to pinpoint the start and end of the 2 tick marks, as well as the start and the end of the feature we passed through. Doing some simple math, we can set up a ratio to find out what our actual feature size is, and here we find that we are able to reach 59.67 over 5, which is 11.93 microns.
The portability requirement, which was that the system had to fit through a door that was 28 through 32 inches, and we passed with a value of 15.5 inches. The next requirement that we have in our final testing is lightweight, which is a requirement that the system shall weigh no more than 50 pounds. At the moment, we have it in progress. It was 4.2.4, which is standard power. We successfully were able to demonstrate that the system works by being plugged into an outlet. Next up, we have requirement 4.2.5, which is the wafer patterning requirements. This is our expected outcome that was mentioned at the beginning of the video, and by design date, we have fully accomplished it. Currently, it is in progress. We expect to complete final testing by Tuesday, November 25th. The next requirement we have passed is 4.3.1, which is UV light stability. We have passed this via inspection through our manufacturer specifications. This requirement required us to have a UV that was within the 410 nanometer range, and our manufacturer specifications give it a range of 405 to 410 nanometers, so we have successfully passed that one. Next is requirement 4.3.2. This requirement is titled self-contained, so this means that the whole prototype has to be within an enclosure. We are fully on track to complete this by design date. Next are 4.3.3 and 4.3.4, which are digital physical stops. Both were passed via data sheets, which our sponsor has successfully signed off on. Lastly, we have our interface requirements, which we have successfully passed both. We have 4.4.1, which is interface, which is that the SEMILITHO has to be able to successfully interface with external devices via data transfer, which it does, so we passed that. And we proved this via the images being sent to the component and being able to see it projected out. And 4.4.2, which is application. So this is that the SEMILITHO shall have an interface with the laptop using an application that allows for access to the system. This is also done via the image being projected, because in order for the image to be projected, it has to be connected to the laptop, and it was sent through that user interface. So those go hand in hand, and we have successfully passed both, as you can see in these images. In this section, you will see a video of our project functioning in the clean room. This is when we completed preliminary testing, and as you can see, we have the prototype in the lab. There's a wafer on the stage, and it is currently being patterned. You can tell that the prototype works because the LED is being turned on. However, the pattern itself is extremely small, so you're not going to see a lot of actual images being processed, but it is happening. It's just on a very, very small scale. So we have included images of the team in the clean room to show our testing process, along with the video of the prototype.
With that being said,
Thank you!